1, 2, 3, 1, 2, 3, 1, 2, 3. Audio input capture. 1, 2, 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. I think that should do the trick. 1, 2, 3. What the okay. Are we getting anything this way? Anything. Okay, great. I recently moved, so everything about my setup is a little bit different. So, bound to be a little bit of, struggle like that. How's everybody doing? This homework set we did covered a lot later than others. Are people mostly done? Have people gotten a good ways through it already? Let's take a look. Let's take a look and join. Okay, so if anybody wants to, if anybody wishes to join the discussion live, you can feel free to hop in to the Discord channel. But otherwise, what problem would you all like to start with? Have you all gotten a chance to look through it? Have you all gotten a chance to take a crack and figure out what problems seem difficult, what problems seem relatively manageable? I think somebody told me that, yeah, number one's the hard. Number one is the most popular problem. Yeah, number one I looked a little bit last evening, and it took me a little while to figure out. The surprising thing about it, in my opinion, is that it really involves, I would say, very little actual calculus. It's almost entirely an algebra problem, I would say. Let me see where I put that file. Let's see. Okay. Number one. Let's open it, and let's zoom right on in. So, okay, I hope you all have number one pulled up. So let me ask you where you're struggling with this problem. Do you understand the basics of the given proof? So they give you a proof for a constant definition of local constant function, and they ask you to sort of extend this proof to the linear case. Does it make sense to you all how exactly the given basic proof works? So does the example make sense to you in the first place? Oh. Hi, I see that someone's joined us. Are you saying anything? Hey, it's going all right. I honestly have no idea if you're being looped to... Can you say something again? Yeah, I have no idea how this is. I guess when I changed my setup a little bit, all of my audio inputs and outputs somehow changed as well. And right now it's very odd. I have no idea if you're actually being broadcasted. If you're actually being broadcasted or not. Let me try to fiddle around with my settings a tiny bit more. But in the meantime, tell me, how do you feel about this problem? Have you taken a good crack at it? Problem one. This is the one that most people are saying is the hard one.
I haven't even sort of dissected that one. It's a long one though. I just want to say a good heavy back.
Oh, sure. Thanks. Okay. Let's see. Can you say just test something a little bit?
Yeah,
can you talk
test.
Go ahead. Say something.
Oh yeah, I did.
Okay, yeah.
Test
It
one,
looks
two,
like you're
three.
being broadcasted. Good. Okay, all right. So I hope you've all had a good break. Wait a minute, you all are in Canada. Canadian Thanksgiving's a different time, right?
Yeah,
Okay.
we had ours a while ago.
So late November, you don't even have a break. Is that right?
Late November? I don't think so, no.
Okay. Most colleges in the U.S. get that week or at least a couple of days off.
Oh,
But to go through this problem, first I will sort of visualize what the heck the original proof is actually talking about. Right? They give you a definition of locally constant. And let's visualize this with a number line. It's basically saying that some function f is locally constant on the interval a and b if for a little interval around a, it's got a constant value. Let's call this constant value c1. And a little bit around, or maybe let's call it ca instead. And a little bit around b, it's also got a constant value. Let's call this cb. And notice how I drew them at kind of slightly different heights to indicate that they may or may not actually be the same value. It's not very clear right now, right? It's possible that, or it might be possible that maybe CB is a little bit greater than CA or a little bit less than CA. It's not immediately clear from the definition itself whether or not they're going to be the same value. It turns out that, in fact, they will be, and that's where the bulk of this proof comes from. And the last thing about the locally constant is that for any other value, they call it x, that's in between a and b. There's a little bit of an interval on each side where, again, it's got a constant value. Let's call this one cx. So ca, cb, and an arbitrary cx for any point on the number line. These constant, it's basically saying that around each individual point, it's local for a little neighborhood. And we're trying to see if in fact this implies that the entire thing must be constant. So does this sort of big picture make sense? Like, I know that reading the problem, it's extremely hard to parse all the dense mathematical notation, but I'm trying to get at the idea here. Does this definition just sort of, is it clear from maybe visual intuition or a picture what exactly is happening here? Anyone from the chat or anyone in the voice channel, please feel free to give some feedback, because it's very essential that we understand what the heck the basic definition is before we move on, right? Makes sense? Okay, I'm getting some affirmative. How does everybody else feel? Let's use the whole 0 to 10 scale. On a scale of 0 to 10, does this definition, make sense to you? Dago, how do you feel? Yeah, makes sense. Good. All right. Well, we got some affirmation, so let's move on to the next bit. So what exactly is this proof doing? It's basically saying we want to show that, we want to show that given that a function satisfies this definition of locally constant, we want to show that, in fact, it's constant on the entire interval. Basically showing that every one of these constant values, cx, ca, cb, we want to show that these are all equal. And intuitively, this kind of makes sense, right? It's sort of saying that, like, if every value is like constant and the same as every other value near it, or rather, you can kind of think of this as like a x and y axis, right? Like f of x is equal to y. And the idea is saying that if every single value maps to, if like every x1 and x2 that are super close to each other map to the same value, you can sort of kind of imagine how this kind of propagates through the entire domain so that everything maps to the same value and that everything is constant. But it takes a little bit of hard work to make this notion precise. So let's try to go through their example and see how to make this precise. So here's how they do it. They start by saying let S, so they're defining some set capital S, and my handwriting is going to be a little bit bad, so just try your best to distinguish a capital S from a lowercase s. Maybe I'll draw an underline to denote that these s's are capital. So this is the set of all s, let S be all little s between A and B, such that there exists a constant C. This is the symbol there exists. There exists a constant C such that f has constant value C on A to S. So this is basically saying S is all of the right endpoints. Yeah? So if we look back on this original image right here from A to B, this is basically saying if this entire segment right here, if everything here has constant value and it ends at this right endpoint, and we call this point S, then this little s would be inside the set big S. So the set big S consists of all the right endpoints of intervals that map to the same thing. Does that make sense? So if we draw this as like a 2D grid, this is basically like saying if every single value in here maps to the exact same value, like f of x is equal to c, then we would say that this right endpoint, little s, is inside big S. That's the idea here. So little s are sort of the right endpoints of partial intervals. Does that idea make sense? This one's a little bit hard to grasp. I want to pause for a moment to ask if people are understanding what the heck this is on about. So maybe I draw a couple more examples, right? How do I put it? So let me draw a couple of... How do we want to do this? Let's say that, from a 0 to 1 example, let's just draw an example of 0 to 1. And let's let an example function, g of x, is just equal to, let's say it equals 1 for x less than or equal to 0.5, and 2 for x greater than 0.5, right? So it's kind of a step function like this. And the idea here is that you can basically consider you can consider the left endpoint being 0, and you can basically consider every possible right endpoint. So every single one of these values here is a valid S value, because the entire left-right interval is constant, right? The entire left-right interval maps to a constant value. In particular, has value 1. But once you start getting over here, it's no longer the case, because if you have something like 0.75, right, the interval from 0 to 0.75, well, it starts to map to 1, 1, 1, 1, 1, but then you cross over and it starts mapping to 2, so it's no longer constant. So you don't have every single thing inside this interval mapping to the same height. So 0.75 is not an element of capital S, but everything else is. So capital S is basically, it looks like 0 to 0.5 for this particular toy example. Hopefully that's not too crazy. Does that make sense? Well, yeah. So the way that this proof works, I wanted to spend some time visualizing this stuff because that's where most of the hard work is, I would say. Once we have these definitions in our head, the rest of it is quite a bit easier. So if S is the set, again, S is the set of all right endpoints, little s, such that A to S, they write it nice and precisely, such that X is equal to C for all X element of A to little s. So they're basically looking at the set capital S now, and they say, take W to be least upper bound, which is in mathematical language called the soup. I hope you've been introduced to the term soup before, because otherwise this might be a little bit confusing. But the idea here is that for every bounded set, there's going to be an upper bound for that bounded set, and in particular, there's going to be a least upper bound. There is no proof for the statement. This is just an axiom that mathematicians have, by agreement, decided is obvious enough to where everyone just decides that this is something you can do. And hopefully that seems reasonable. Yeah, hopefully that seems reasonable. On my end, my internet's getting a little bit laggy right now, so do let me know if the stream quality is being affected. But the idea at this point is, once we have the idea of W being a least upper bound, we want to show that W is equal to B. And once you show that W is equal to B, you are, I think you're basically pretty much done. Because if B itself is an element of S, then it follows that everything from A comma B is constant. Or every x element of B has f of x constant. So this is the big statement that we want to show. We want to show that W is equal to B. And the way we do this is by ruling out the cases. We want to rule out the possibility of W being equal to A and W being between A and B. So we want to rule these out. Yeah,